Hello everyone, welcome to the next MCAT ACE lecture in our series, and this one is on thermodynamics. So let's take a look at the outline together. So the general outline as to what we want to cover here, we're going to take a look at systems. That includes open, closed, and isolated, and what those types of systems refer to and what they mean. We'll also take a look at state functions briefly. Then a lot of the body of the material we're going to be looking at discusses the 4 laws of thermodynamics, which you want to be familiar with, along with the concept of work being done through pressure-volume relationships. So you can think of something like a piston in relation to that. And then we're going to take a look at heat and heat transfer, which will include heat capacity and specific heat. We're going to take a brief look at heat transfer and what the difference between temperature and heat is, along with the different types of transfers we may come across. And then we will also discuss enthalpy. So some people know that as delta H when we're using the thermodynamic abbreviations, and that also ties into the larger thermodynamic equation for free energy. So we will certainly be talking about enthalpy, entropy, and Gibbs free energy when we take a look at this entire lecture. And then obviously at the end, we will have our practice session as usual. So let's move forward and start taking a look at our thermodynamic systems that could be possible. So first of all, what is thermodynamics when we consider it in a broad sense? It's the study of energy, and usually that's going to be from work or heat. And it's going to involve interactions between systems and their surroundings. So when we have a system, that's usually going to be considered something with a boundary that has a specific set of reactions or heat exchange that's of interest to us as the observers. And then we will consider everything else usually to be the surroundings. So the surroundings can include everything up to the known universe and its borders or its limits as it's continuing to expand. But a lot of times we think of it in a more immediate sense. So let's say we have a reaction vessel and that reaction vessel is buried inside of a hot water bath. Then we'll consider the hot water bath to be the immediate surroundings, even though that hot water bath is also in contact with the direct environment in the room you're in, which is in direct environment with the school or university or wherever you might be, which is part of the larger universe. So the system is very much a smaller component, generally speaking, in comparison to the surroundings. Now, what type of systems can we talk about? So an open system is going to be one where there is open exchange. So you can think of it just like a door that's allowing things to flow in and out. Now, what can we exchange? We can exchange heat, right? Forms of energy. We can exchange physical matter, and there can be work done with the surroundings when we have an open system. So it is by far the one that allows for the most transfer readily back and forth between systems and surroundings. Then you have a closed system. For a closed system, you're going to take away that exchange of matter, but you will still be able to have exchange of heat in a closed system, right? So again, getting into a more simplified model, all right? Imagine that you have a door that's got a very nice seal on it to your house, and there's only that one door. As soon as you close it, the house is still in direct contact with the environment on the street you live in or whatever else. So there can still be a readily exchangeable form of energy between the house. It gets cold, it gets hot, depending on the environment outside, right? However, when you try to get matter in or out, if that seal is very good on the door, you're not going to be able to bring any matter in or out of the house. So whatever's in the house stays in, and whatever's outside is outside. Okay, then we get to an isolated system. This is where there's no exchange of heat, work, or matter with the surroundings. Okay, but when you take a look at an isolated system, these tend to be very difficult systems to find outside of a very strict laboratory setting or something like that. They're a little more hypothetical in nature. Certainly you couldn't have a house or some other general item you would come across acting as an isolated system. Now, you have some that represent an isolated system a little bit better. So maybe when you get some of those expensive hydrothermal flasks or a very well-built cooler or something like that, right? It's doing a good job in terms of not allowing a whole lot of heat transfer to occur. Some of those can, keep drinks hot or cold for hours on end before there's really a massive or noticeable heat loss or difference. However, over time, those would still be considered closed systems and not isolated systems, because with an isolated system, if it's at a specific temperature, it has a certain amount of internal energy in that system, that's going to remain constant until that isolated system is no longer isolated. It has to at least be moved over to a closed system, if not an open system, in order to start seeing differences like that. So here's just a brief picture. You can see the surroundings, right? This little sort of light blue square is going to be considered everything else around it. And then we have the different types of systems. So a system that's open, you get the energy and the matter that can be exchanged. Work is very readily done between the surroundings and system. So the surroundings can do work on the system can do work on the surroundings. It goes vice versa. Then with the closed surroundings, you're only dealing with the energy. Remember that heat is a form of energy when we're looking at that. And then in isolated, you see there are no arrows, and that's because there is no transfer back or forth. All right, so a state function. What is a state function? There's going to be several state variables or quantities that depend only on the current state of the system we're looking at. So when it's in an equilibrium state, that is when we're referring to a state function, something like enthalpy, okay, delta H, which we're going to discuss later. A state function is going to be path independent, so it only is going to rely on the current state that you reside in. So one of the best ways, and this is the picture that I use down here to represent this, one of the best ways I can explain this is, let's imagine that you have a mountain that you need to climb. And when you're trying to climb this mountain, there's two different paths to the top point or whatever point you're trying to get to. The first path is very, very steep, but it goes almost directly up to that top or that point that you're looking for. And then the second path is very long, and you go around and around. It's spiraling around, but it's a slower climb. It's not nearly as steep, okay? There are going to be different paths that you can take to get to that point. But whether you are a person who took path A or path B, it doesn't matter at the end because you are at the same point. All that matters once you're both at that point is that you arrived at the same current equilibrium state. And that's sort of a relationship that you can draw between state functions and something that you can imagine, all right? So imagine these hikers, they're climbing up to the top of the mountain. The only thing that matters is that top of the mountain point, all right? So with something like enthalpy, when we're breaking bonds and forming bonds, there might be a whole lot of different ways we could break and form bonds to get to the products of interest. Maybe one reaction only uses 2 steps and another reaction uses 15 steps. But between all the bonds that break and all the bonds that form, if we started with the same reactants and ended with the same products, no matter which pathway we took to get there, all that matters overall is the fact that we currently reside in either the products or the reactants or whatever equilibrium state between those exists, okay? So state functions, as I've started mentioning, can include enthalpy, that's delta H. It can include entropy, delta S, free energy, delta G, and then delta U, which tends to be spoken of a little bit less just because it's not always in all the equations that we see for free energy, but that's internal energy change. So again, going back to those systems, I was discussing in an isolated system internal energy and how it would remain constant there because you have no exchange back and forth. Okay, so delta U, there is a internal energy associated with systems. So now that we have an idea of what a state function represents, we know a couple of them, and we've also got a general idea of systems and surroundings, let's discuss the laws of thermodynamics that govern these systems and surroundings and the ways that they can interact with one another. Okay, so for thermodynamics, we have 4 fundamental empirical principles, and they are known as the zeroth, the first, the second, and the third law. All right. Now, most people are probably, and I say most people outside of science are probably most familiar with the first and the second law. And there's different ways of stating them, but the most common one that most people understand for the first law is energy cannot be created or destroyed. That's really the conservation of energy, which is a separate thing, but it plays into the first law. And then the second law is disorder or randomness is always increasing, or entropy always increases in a system. So let's take a look at these in more detail. So what is the zeroth law? The zeroth law has to do with thermal equilibrium, and it says that heat flows from hot objects to cold objects in order to achieve temperature equilibrium. Right? And according to the zeroth law of thermodynamics, when you have 2 systems in thermal equilibrium and then you introduce a third system, they're all going to work with one another in terms of heat flow, and they're going to in turn be all in equal thermal equilibrium with each other. So you can see here, this is one of those A is to B, and then if B is to C, then C is to A type of relationships. And this is important because it also plays into part of the second law of thermodynamics, which is talking about increasing entropy in a system. Go back up to this top part. Hot objects to cold objects, okay? So heat is always going to be flowing from hot to cold. We're trying to warm up. So a cold system is going to have more structure, more order, less energy. And so because we're going to constantly try to increase the entropy based on the second law, we've always got heat flowing from hot objects to cold objects until there's a thermal equilibrium, right? And that makes sense because if you have a hot object and a cold object, it would make sense for the hot object to transfer all of its heat over to the cold object so that that cold object is then burning hot, and then you have the original hot object is cold, because then you just start sending it back the other way, right? They're going to continue to go until they hit some sort of a thermal equilibrium. And then we also know if that was in an isolated system, these, A, B, and C, that's one thing, but those are also in contact usually with the surroundings. And so when we have the surroundings, the systems, provided they can have heat transfer with the surroundings, they are going to basically cool to the temperature of the surroundings, and the surroundings will attempt to warm up to the temperature of these objects. Or if the surroundings are warmer, then vice versa. So, the first law of thermodynamics, right? Now, this is the one that has a little bit to do with the conservation of energy. So you can see here it says it's based on the principle of the conservation of energy, and that states you cannot have any type of destruction or creation of energy. It can only be transferred or transformed. And then when you look at that, okay, this is based on the principle of conservation of energy. It states that a change in total internal energy, which we spoke about a minute ago, delta U, or delta E sometimes, of a system is equal to the contributions from heat and work. Okay, so there are 2 things that can contribute to the total internal energy of a system, and that is heat and then work. All right, so you can see this sort of little flowchart diagram here. On the left, we have heat is absorbed into the system, right? That's plus Q. Q is the letter we tend to use to represent heat energy. So that would be a plus to the system. And then if heat is lost from the system, it's minus Q. If work is done on the system, think of a piston being compressed, right? If work is being done on that system, it's positive. And then if the system is going to do work on the surroundings, some type of expansion, then it's losing energy and giving it over to the surroundings, right? So that's what the first law really states. So yes, it is that you cannot create or destroy energy. It can only be transferred. We're looking at the first law in terms of how can it be transferred? What is it that really composes the internal energy of a system? All right, so now we have the second law of thermodynamics. And this defines entropy. that we've been talking about. So that's the delta S. And there's lots of different terms that you can use for entropy. One of the most common ones is disorder or randomness. That's a common term that people like to use when describing it. And specifically, entropy is the disorderness or randomness of a system. So the second law is going to be defined in a couple different ways, and you can look here at this list that's made. So the entropy of an isolated system will increase over time until a maximum entropy is reached. Okay? The systems tend toward equilibrium with their surroundings, and the entropy of a system that is in equilibrium with its surroundings will remain constant. Entropy, this is the note at the bottom here, for states of matter. Gases are going to have the highest entropy, then liquids, and then solids. And that makes sense if you think about the molecules, the amount of space separating them, and the motion that is associated with them. Gases have lots of space in between, and they have incredible amounts of random motion. It's very chaotic. Liquids are far more structured than gases. You've got a whole collection with relatively little space in between. However, the molecules are still fluid enough, right, to move over top of one another and give it that extra boost of entropy there. Whereas solid material is highly structured. That does not mean that it has no entropy, but the atoms are very close to one another. There's usually only room for vibration in comparison to liquids. So most solids, there are semi-solids, and you can get into some of the physics of that, but most solids are going to stay in a solid state, and they're going to be able to vibrate and move even when you're not like hammering away at them, right? Bonds have vibrations, but they are far more structured in comparison to the other two states of matter, right? And then entropy is going to increase as the thermal energy inside of a system increases. And that makes sense because if I have a solid, let's take water for example. If I have an ice cube, I have to allow heat, thermal energy to transfer from the surroundings into the system, that ice cube, in order to melt it. So let's say that I take the ice cube and I set it out on the countertop, right? So as it slowly melts, let's say I put it in a pot, and I lay that pot on the countertop. As it slowly melts, it's taking some heat from the surroundings, the pot, the counter, whatever it might be, and that's increasing it from a solid to a liquid in terms of its entropy, right? And then I could add additional thermal energy and boil it into a gas, and that would do the same thing. That would increase its entropy once again. So here's a perfect example like we were just talking about. You have the second law, less entropy and randomness, the ice cube with tightly packed molecules. The water, it gets a little more fluid, there's less tightly packing going on. And then when you get to the steam, it's all over the place. You've got a lot of entropy and randomness in the molecule motion at that point. All right, so now for the third law of thermodynamics, and this is the one that tends to be a little more difficult to explain to students. This law was also, it is considered one of the laws, but it was one of the ones that was more highly debated for a while, until more recently when mathematical theorems have been able to solidify this and prove it. So the third law of thermodynamics states that as entropy approaches entropy will approach a constant value as temperature approaches absolute zero. So the closer you get to absolute zero, your entropy has to come close to a constant value, which means you're essentially going to have to freeze your entropy and no longer allow it to grow. And this is obviously a difficult suggestion to grasp because we just got finished talking about how the entropy will constantly be increasing in a system with the second law of thermodynamics supported by the Zeroth law. So as absolute zero is neared, there's something referred to as the crystal state. So think of a crystal, highly ordered and highly structured, okay? And matter will go into this crystal state as you approach absolute zero, where essentially all of the molecules have perfect formation and there is only what's known as residual entropy left. So there's not a whole lot of motion or even vibration. You're just at a standstill. There's very, very minor entropy left. Right? Now, this is the part that's a little difficult for people to grasp sometimes. Absolute zero is an unattainable value due to the second law of thermodynamics, right? Entropy is always increasing and warmer systems are flowing to cooler. So why is absolute zero? And remember, when we're talking about absolute zero, Kelvin is the absolute scale. So we're talking about 0 Kelvin, all right? When we get to 0 Kelvin, why is it unattainable and it's just a theoretical construct? Now, we have in labs had the ability to get, I believe it's to like a millionth of a degree of 0 Kelvin. So we're very close. But the problem mathematically is, as you continue to remove thermal energy from a system, it's requiring more and more energy from the surroundings to pull that thermal energy out of the system. Because keep in mind that the warmer system / surroundings wants to go and start warming up the cooler one. So as you get colder and colder, you're fighting against entropy more and more, where there's a greater desire for the flow back into that cold system, right? And the reason this is impossible is at the end, when you get to absolute zero, you would technically need an infinite amount of power to pull that last bit of thermal energy out of the system. And we obviously do not have sources of infinite pulling power or an infinite number of steps that we can continuously pull from. So we can get very close, but absolute zero is, as far as we know right now, an unattainable process. We can get very close, but we cannot get to absolute zero. All right, so those were the main laws of thermodynamics, the 4 that we wanted to take a look at. So now we're going to take a look at a couple other concepts. We'll look at pressure, volume work, and then we're going to start moving into thermal energy with heat capacity and entropy. Enthalpy, along with entropy. So, pressure, volume work. When we have these PV diagrams, they depict the thermodynamic process that's plotting pressure against volume. So most people are familiar with pressure and volume from gas laws and things of that nature. They share inverse relationships with one another. And when you plot pressure versus volume on your graphs for thermodynamic work, the area that is found under the curve there, so you can see this right here, is going to be work done from point A to point B. So if you can find the area under that curve, that's the work that has been done from a pressure-volume relationship. All right. Now, let's discuss the type of processes that we can have when we're dealing with these types of situations. So there is something known as an adiabatic process, which is where no heat is exchanged. So if no heat is exchanged, remember the first law of thermodynamics tells us the internal energy is heat plus work. So if no heat is being utilized and Q is equal to 0, then internal energy simply equals work when we have an adiabatic process. You have isothermal process, and that's where there is no change in temperature. Okay. You have isobaric process. That's where the pressure is held constant. That doesn't mean that there's no pressure. It just means the pressure is not going to change. And then you have isovolumetric process, and that's where the volume is constant. And you can see this graph over here, right? If we have the pressure versus volume again, you have isovolumetric just going up and down because the pressure can change along the y-axis, but you're not going to have a change in your volume. It's going to stay at the same x point. And then we have the isobaric process over here, and when you're looking at that, you can go across the x-axis, but the pressure is sort of nailed down to a specific point on the y-axis for the pressure there. So heat capacity is a term that's used fairly often along with things like specific heat. So what is heat capacity? Heat capacity is going to be the amount of heat that an object is going to need in order to change the temperature of the object by 1 degree Celsius, okay, or sometimes 1 degree Kelvin, depending on your units and what value you're looking at. So the general unit for heat capacity is going to be joules per degree Celsius, because joules is our energy, so we need to know how much energy is required per degree Celsius that we want to change that object. Okay, and then based on the actual chemical composition, each object will have its own heat capacity. So aluminum and iron and zinc will all have different heat capacities from one another because they are different objects, they are different chemical structures, so they'll require a different amount of energy to be raised 1 degree Celsius. All right, so heat capacity is Q, that's our heat energy, over delta T, which is the change in temperature. Anytime you see that delta, that's change in temperature. Now, other definitions you may come across, and sometimes these can be more useful because they get a little more specific. You can have molar heat capacity, which refers to the heat capacity per mole of substance. And then you can also have specific heat capacity, and that's going to refer to the heat capacity per mass, so per gram of substance. I would say specific heat capacity is the one I come across most often when we're dealing with how much energy would it take to raise 1 gram of one material 1 degree Celsius. Okay? Especially water is a very common one that you'll come across. And in fact, you'll see that in one of the examples that we have when we practice at the end. So heat versus temperature. This is always something that confuses people when they first learn about thermodynamics. Okay? Heat and temperature are not the same thing. And a lot of times we'll sort of use them interchangeably in everyday slang. We'll say, oh, it's hot out, and we'll say there's a lot, there's a lot of heat out there when we might be referring to or talking about temperature, but they certainly are intertwined. So what is heat? Heat is the total amount of energy of motion in the molecules of a matter that can be transferred from one object to another. So heat is really the energy itself, okay, that can be transferred back and forth. Temperature is referring to the average amount of energy of motion for the molecules in the matter. So temperature is an average reading of the motion of the molecules, okay, whereas heat is the total amount of energy for the motion in those molecules that can be transferred back and forth. So speaking of heat transfer, right, and that's how we get changes or delta T's when heat transfers back and forth, there's several types of heat transfer that we can discuss or talk about. All right, so the 3 types that we're going to talk about here, the first one is conduction. So this is heat energy that is transferred by direct contact, requires things to be touching one another. So you can see in our example down here, we've got a hand that is touching the pot. And most people have had this type of experience where they go to grab a hot frying pan or stainless steel pan, and if you're not wearing an oven mitt and you directly touch the handle, sometimes you can feel that heat. Sometimes it's too hot to touch. That's through direct contact with your skin. That would be an example of conduction. Now, convection is when heat energy is transferred by a flowing current. So coming back to our example here, you've got the hot water that's being held over the fire. As this water heats up, right, you can get heat energy that is flowing like a current through the medium of water, right? Now the last one, radiation, is heat energy that's transferred by electromagnetic radiation. So that differs from the convection because the radiation doesn't require a physical flow of matter like the water, and it can occur in a vacuum, right? So you have something, and through electromagnetic radiation, it's transferring that heat. It doesn't need the water or some other source in order to get that current flow going. And you can see that example here with the pot being held far above the fire and the radiation, right, is coming off of that fire there. So endothermic and exothermic. Let's discuss these two because these terms are used quite often when we get into enthalpy and thermodynamics. So exothermic reactions are going to be reactions in which energy is transferred from the reaction of the system into the surroundings. So we always think about exothermic reactions give off heat, right? So that's being transferred from the system to the surroundings. That's why we can feel it. We say it gives it off because we, as the observers, are part of those surroundings. We feel the heat coming off of the flask or whatever other type of system we have. And then endothermic reactions, energy is absorbed from the surroundings. And when you do something like that, you can actually feel that it is cold when it's taking the energy out from the surroundings. All right, now look at these graphs here. We have potential energy. Look at the reactants and the products. For something that's exothermic, all right, the energy starts off high here with the reactants and it moves to a lower point with the products. So energy had to have been released if we're at less energy when we get to the products. And then when we come here to the endothermic reaction, we have lower energy for the reactants and higher energy for the products. So we had to absorb energy, right, when we got to this point here. Now, you can also see activation energy, EA, okay, and that is a term that's used for this highest energy point in the reaction. And it's the amount of energy that is required if you're climbing this mountain or this hill until you reach the sort of tipping point where then you can fall and hit your products on the other side. So it is literally the energy required to activate this equilibrium state and get moving toward your products. Now, if you look at the exothermic and endothermic situation, in the endothermic you have a much larger barrier that you have to overcome here for the activation energy in comparison to the exothermic, where you have a smaller one because you're just going to be releasing it here. So endothermic and exothermic tie into enthalpy, which is something we've been talking about for quite a while now. So enthalpy, or H, is going to be the heat content of a reaction that can be expressed in units as energy, like joules, or in energy per some unit, usually energy per mole. And for exothermic reactions, the change in enthalpy is going to be negative, while endothermic reactions, the change will be positive. So many students, when they're in general chemistry, they learn a delta H that is negative is going to be exothermic, whereas a delta H that is positive is going to be associated with endothermic. Okay, and that's for releasing, negative, that's exo, and absorbing, endo, that's positive, right? You would gain towards the system in an endothermic situation. And there is something known as Hess's law. We're not going over a specific example right here, but you probably remember this from your classes. When we had Hess's law, this is where you would take several different chemical equations and you would flip them back and forth so you'd get the proper signs, and then you'd multiply by the coefficients that you needed to get the correct molar ratios, and then you'd cancel everything out in order to give you the final equation that you were looking for. And then you would sum all of the delta H's, and those would come out to the total delta H associated with that reaction. And this is a perfect example of delta H being a state function, because there's multiple reactions you could go through, but if you add up all the broken bonds and all of the formed bonds, you're still going to end up with the same delta H if you have the same starting point and ending point. All right. So it says, regardless of the number of steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. That right there, it's a state function. Now, free energy, okay? Free energy is the available energy that can be converted to do work. And this is probably the overarching energy concept for thermodynamics. We usually start speaking about free energy and delta G when we start looking at things like, for instance, in organic chemistry, when we start taking a look at reaction diagrams and timelines of reactions, a lot of it will be measured with free energy. Right? Now, the calculation for free energy is delta G equals delta H minus T delta S. So change in free energy is equal to change in enthalpy subtracted from the temperature and the change in entropy, where G is free energy, H is enthalpy, heat content, T is temperature in Kelvin, and S is entropy. That's the disorder or the randomness of the system there. All right, now, very important point here. When we want to decide whether a reaction is going to be spontaneous or not, we have to take a look at the free energy content. A lot of students will have a habit of trying to look at just the enthalpy and based on exo or endothermic determine whether a reaction is spontaneous or not. Because if you go back and you look, right? It's very easy to say, well, this one would be spontaneous because you're going downhill and releasing energy, whereas this one is not spontaneous. You require a lot more energy to be put in, and it is higher energy. And that's good. However, if you notice, delta G is not directly equal to delta H. There's another portion to this equation here that has to be considered. And so we can't always share that direct relationship with delta G and delta H without considering the temperature and the entropy. Okay? So when we get to free energy, a decrease in free energy, where delta G is going to be less than 0, corresponds to a spontaneous reaction, while an increase in free energy, delta G is greater than 0, or a positive value, is going to correspond to a non-spontaneous process. So that's very important when you are assessing and looking at delta G in relation to whether a reaction will be spontaneous or not. Okay, and that wraps up our lecture for thermodynamics. So now we're going to head over and we're going to start some practice questions, and then we'll wrap everything up from there, and we will be all set with the thermodynamics part of the course. Okay, so I have brought up the questions here for the thermodynamic course, and we're going to go through these briefly. And as usual, you go ahead and pause the video lesson, try to work them out yourself, or at least get as far along the way as you can, and then we will walk through them together before wrapping up here. So, number 1, the process of dissolving ammonium nitrate in water is an endothermic process, and you see the equation given there. A little more detail. When 1.8 grams of ammonium nitrate was dissolved in 50 grams of water, the temperature was observed to decrease by 2.70. Given the specific heat of water is 4.18 joules per gram Celsius, what enthalpy change is expected to occur when 1 mole of ammonium nitrate dissolves completely in water? Okay, and then right here you have your options: 11.3 joules, 209 joules, 19.4 kilojoules. Notice the difference between the joules and kilojoules when you're picking out your option here. And 25.1 kilojoules. All right, and then question 2. Compounds A and B undergo an exothermic concerted, which means one-step, reaction at 25 degrees Celsius to afford compound C 75% along with compound D 25%, which is a constitutional isomer of compound C. So you get a mixture there. A 40-60 mixture of C and D is produced when pure compound D is heated to 100 degrees Celsius for several hours. Which one of the following statements is most consistent with the given information? So you're going to have to pay very close attention to the wording in these answers. A, if the reaction is subject to kinetic control, heating pure compound C at 100 degrees Celsius is expected to afford a 40-60 mixture of C and D. B, the more stable reaction product, C or D, is formed faster than the less stable product, D or C. So it's saying you pick C or D. You have to make your choice there. An equilibrium mixture of compounds C and D at 100 degrees Celsius contains 40% C. And finally, D, both compounds C and D are more stable than compounds A and B. So those are the questions for you to work on for the thermodynamic lecture here. So I'll scroll through them again one more time. You can pause it if you need to copy anything down. And then, again, do your best to work through what you can without unpausing the video. And then once you feel that you're at a point where you're ready, go ahead and unpause it so we can go through the walkthrough. All right, so I hope everybody had a good chance to attempt these problems here. So let's go through now and take a look at the answers for both question 1 and 2 and where we're coming from with this. So for question 1, we have a process of dissolving ammonium nitrate in water. It's an endothermic process. And because of that, we would expect that there's a positive heat association with it, meaning the system took heat in. All right. Now, they give us details here, and we are trying to work with heat capacity because they're giving the specific heat of water, plus they're giving the mass of ammonium nitrate. So the way that we want to work this out is that we could have C equals Q over M delta T. And we can rearrange this because we're really looking for Q in this case, because C is already given to us at the 4.18 joules per gram. What we want to find out is what enthalpy change is expected. So we need to get a hold of the joules value, which is going to come directly from Q, which is our heat value. So we can algebraically rearrange this equation so that we end up with Q equals the mass times the heat capacity times the delta T. And if we arrange it in this way, we can then plug our values in. So Q is going to be equal to, now you have to be careful what you choose for mass here, all right? A lot of students want to go for the 1.8 grams of ammonium nitrate, but what you have to realize is you're looking at the temperature difference of 2.7 here, and that's the temperature difference of the water that you're taking, right? It's not directly of the ammonium nitrate. You're measuring the water change, and the ammonium nitrate is what was dissolved in that water. So we really have 50 grams of water. So make sure that you're paying attention to what mass you're throwing in here. Now that 1.8 grams will become important in just a minute, but not yet. So we're going to multiply that by the heat capacity of water, which should be another giveaway, right? If we're using water's value in here, then we need the mass of water. That's how this would work. Joules per gram Celsius. And then the final thing that we need here is the temperature difference, and that is 2.7. Now in this case, the values they're giving are Celsius. And so we would also put Celsius here because our units have to cancel. You may find values that are given in Kelvin, or sometimes you may find them given in Celsius. Just keep your units consistent when you're working through this. So if you work through your math there, you end up with 564.3 joules. Now, this is not the final answer. That should be evident because you don't even see that answer present over on the left. So we're going to need to do something else with this. This right here was for 1.8 grams of the ammonium nitrate, right? So this amount of heat is the amount that was absorbed for 1.8 grams of the ammonium nitrate. Now the question is, what about 1 mole of the ammonium nitrate? Right? So this is a fairly simple process, but what you will need is the molar mass of the ammonium nitrate. So if we go back up and take a look, here is the ammonium nitrate. So you would need the molar mass of this, and you could do that. Remember that nitrogen is equal to 14, okay, and we're going to use approximate values here. Hydrogen is equal to 1, and oxygen is equal to 16. So if you did some quick adding and multiplication, you should come up with 80 grams per mole when you were working on this. So what we would do at that point is we would say, all right, I want this to be in joules per mole, right? Because it says when 1 mole of ammonium nitrate dissolves completely in water. So I have to get this relative to the mole amount. Now, it's 564.3 joules, and we know that we have 80 grams per mole. And this would be divided by 1.8 grams, right? Because that's how many grams this value is associated with when we originally ran the 1.8 gram reaction. So if you solve for all of that in joules, you're going to come out with 25,080 joules. And that's joules per mole. So if we look at this, okay, this would be closest to answer D. And keep in mind, kilojoules, right, simply means that we're moving the decimal over 3 spaces, 1, 2, 3. So it would be 25.080. So with rounding and significant figures, you're looking at answer D as the most likely choice here. All right, now, compounds A and B undergo the exothermic reaction. So what we have here is we're going to have a general exothermic reaction where 2 reactants are going to give 2 products in a specific ratio. And then furthermore, if one of those products is heated for an extended period of time, it's found that the ratio of product D increases. Okay, so we have to determine which of the following is the correct answer here. Now, in order to do this, I'm going to bring up a image, and that image that I want to bring up is going to be what's known as the reaction coordinates for what we're looking at here. So what you can see here is the diagram that I wanted to bring up, and this is known as a reaction coordinate or a reaction timeline diagram for usually most organic type of reactions. So what you have is it starts with compound A and B, and they go through their transition state, and then they end up as C and D. So this is something that you could utilize to help answer the question. Notice that we don't have the exact energy units here. This is just a general going theme. However, it's important to note that C and D, the products here, are at different energy levels from one another. And that becomes very important in answering some of the potential answers here or eliminating them. And it's also important to note that because we said this reaction is an exothermic reaction, the energy is going from A and B to C and D, and it's a drop as far as a release in energy. So C and D are lower in energy than A and B, which means that these are going to be more stable. So, going up and taking a look at these options here. Option A, if the reaction is subject to kinetic control, heating pure compound C at 100 degrees Celsius is expected to afford a 40-60 mixture of C and D. All right, now this answer would not be correct. And the reason this is incorrect is this word right here, kinetic control. Kinetic control is referring to the product that forms quickly. So when you're under kinetic control conditions, you're talking about controlling the reaction so that the product that has the lowest energy of activation is going to be the one that's favored. And if we come down and we look here, transition state C is lower on the transition state energy required than D. So it will likely form faster than product D will. But product D is going to be more stable than product C because it's lower in energy. So this is going to be the kinetic product, C, and then D is going to be the thermodynamic product. So if we're talking about a 40-60 mixture of C and D, that's favoring D at 60. And again, we just said that D is the thermodynamic product. So to favor D, we would not expect kinetic control. If we're controlling the reaction kinetically, we would expect to see more C than we do D. And if you come back up and you look here, a concerted one-step mechanism at 25 degrees Celsius, okay, to afford 75% C and 25% D, you can see the kinetic control right there. Now, when we talk about kinetic control and thermodynamic control, it's kind of a sliding scale. So you will have, it's not where you can just switch the kinetic control on or off so easily. Usually lower temperatures, so this is about room temperature here, will give kinetic control. And then as you heat, especially allowing for a decent amount of time, that will start to favor the thermodynamic control when you can establish an equilibrium and allow time for the more stable product to basically overcome that energy of activation and then come to its resting spot down in the energy bottom, so to speak, at the product side. So A is out, especially due to that kinetic word. We're really looking at if that was thermodynamic, then that would make more sense. So let's take a look at B. The more stable reaction product, C or D, well, we just discussed that it would be D, is formed faster than the less stable product, which would be C. So if you were listening to what I just said, this would also be incorrect. And that's because the word faster here, okay, faster is related to kinetics when we're talking about which product will form at a more rapid pace. So to say that the more stable reaction product will be formed faster than the less stable, that's incorrect. In fact, it's the opposite. The less stable product has the least amount of energy resistance to overcome. So the kinetic product, C, is going to form very fast. D, which is more stable, is going to take a bit more time, and you're going to need the thermodynamic conditions set up. All right, now C, an equilibrium mixture of compounds C and D at 100 degrees Celsius contains 40% C. Now this might be an appealing option when you first look at it. An equilibrium mixture of C and D at 100 contains 40% C. That looks appealing because it says up here, when pure compound D is heated at 100 degrees Celsius for several hours, you're going to get a 40-60 mixture of C and D. So you see 40 and C, and then you see that we were heating at 100 degrees Celsius. So we're looking at thermodynamic control here, starting to favor D. Now, while thermodynamic control does open up equilibrium, you have to have reversible conditions for thermodynamic control. Okay, just because it's stating the outcome or the result here does not mean that the equilibrium mixture of C and D at 100 degrees Celsius was 40%. So that is to say, when C and D are in equilibrium, that does not mean that C is going to be at 40%. That is the result of heating for several hours after everything has cooled down and the final analysis has been done. You would need to do sort of a kinetic experiment in order to determine whether this is true, and the equilibrium mixture, as you're in the process of that heated solution being in equilibrium over a period of time, you would want to take several samples and basically set up your own experiment to determine where this equilibrium lies. So while this is certainly better than choice A and B, C still, it's kind of from a lack of information there, that's more of a guess. D, both compounds C and D are more stable than compound A and compound B. This was actually one of the first things we said when we were looking at this diagram down here. If we look at energy, all right, energy and stability are inversely proportional to one another. So here it states that A and B on this diagram have higher energy than both C and D. So really what I consider to be the simplest answer just through observation is the correct one here. So these other potential answers, you had to do a lot of back and forth with looking at kinetic control, thermodynamic control, stability, all of that sort of stuff. D was an appealing answer, and it is the correct answer. Both compounds C and D are more stable than compounds A and B, and you can see that simply from the energy diagram. Now again, how do we know to draw this? Because the reaction told us that we had an exothermic reaction. So we're making a general reaction coordinate diagram here. So that is going to wrap up the questions for the thermodynamic MCAT ACE course. Thank you guys for learning with us, and we will see you for future lectures.